In this video, I'd like to introduce you complex integration. So you might have been expecting this because we covered complex arithmetic, complex trig, complex exponential functions, and then we went to complex limits and derivatives. So integration is coming here. If you have taken multivariable calculus class, this will correspond to what's called line integrals. But you don't have to know that. We'll cover it here. Here we go. Okay, so review of usual Riemann integrals for real functions. So if you have a real function defined on a interval a to b, and let's say it's continuous, then we can define this definite integral as a limit of this Riemann sums. So we are multiplying the height of the rectangles at the height of the function's height and multiplying by the width of the rectangle, and we're going to sum those up. Right? So we're estimating the area underneath the curve and make the estimate more and more precise by using more rectangles. You've seen this in a calculus course. Okay. And then the fundamental theorem of calculus says that if you have a continuous function, then we can define the area function. And then if you take the derivative of this area function, we get the integrand. It's basically taking this area function is like the opposite of taking the derivative. Okay. And since all antiderivatives of a function only differ by arbitrary constant, we usually write as c. The conclusion we can draw is that if you take any antiderivative and look at the difference, the constant cancels out anyway, so we get the area underneath the curve. All right, so let's take this setting to the complex functions. Riemann integrals are on an interval because it's a one-dimensional thing. Complex numbers are two-dimensional. So what we're going to do is we're going to integrate along a curve sitting in the complex plane. So let's say gamma, which is a curve defined on the real interval a to b, and it's going to have the real part and imaginary part. What we're going to do is we're going to define this path integral, this complex integration, along the curve to be function evaluated at some intermediate points on the curve, and you multiply by the change in the location of the intermediate points. Okay, so very similar definition to the Riemann integral that we had before. And the intermediate points is going to be gamma evaluated at those TJ intermediate real time variable. Okay, and what we're going to do is define this integral to be that limit, which will be equivalent to the Riemann integral from a to b of f of gamma of t times gamma prime of t. So let me tell you why they're equivalent. So we are looking at this summation, okay? And these points zj and zj plus 1, those are gamma evaluated at tj, okay? So that's how these terms popped up. And what I'm going to do is multiply and divide by the tj plus 1 minus tj, at top and bottom. So now this factor right here is going to approach the derivative of the gamma, right? Because it's the difference quotient. And the difference in the TJs, these will become the dt in the integration. Okay, so you can turn the complex line integral along a curve into like a real a Riemann integral by using this formula. This formula right here. Okay, so how should we think about complex values? So now we're going through the domain along a curve, so it's a one-dimensional thing. So we can compare it to the Riemann integrals, but the output of the function itself is also two-dimensional. How should we think about these complex valued integral? Well, it's not too different from what we think about in the real integral. Just imagine the real parts and imaginary parts separately, if you like, and do the Riemann integral on both pieces. Right? So if you're integrating e to the it dt from 0 to pi, the real part of e to the it is cosine, the imaginary part is sine of t, so you can integrate both of those separately, and then we can get the result. Okay. Most of the time, you don't really even need to separate it. So if you find an antiderivative of the complex function, you could just plug it in at the endpoints and evaluate it that way. Okay, so let's do examples, a few examples of path integrals. So here, the first path that we're going to look at is t plus it. So I'm going to start from the origin at t equals 0 and go up to 1 plus I when t is equal to 1. And I want to integrate the complex function z squared. So how do we do that? Well, I'm going to use the formula for the line integral. So I'm going to look at the function z squared, except I'm going to plug in gamma, so which is t plus it. And then I'm going to multiply the integrand in the derivative of the curve, so gamma prime, which in this case is 1 plus I. And we can multiply it out, get the constants out in front of the integral. And then now this is a Riemann integral. So we could just compute it, find the antiderivative, plug in the endpoints, and we're done. Okay. Let's integrate along the unit circle, starting at 1 and going counterclockwise. And we're going to integrate the function 1 over z. Now, I'm going to warn you, this is a very important example. We're going to come back to this example over and over again. It's very fundamental in the theory that we're going to study later. So pay attention. But the computation itself isn't bad. We're integrating 1 over z along this curve. So we plug in gamma, multiply by the derivative, and then we're going to go from 0 to pi. Most of the inside cancels out. So e to the it in the denominator and e to the it in the numerator will cancel out. We do have an extra I from the chain rule. We could pull that out. We can integrate 1 from 0 to 2 pi, and we get the answer 2 pi I. Okay. So I said this example was important. So let's compare it with similar examples. So what if the integrand is not 1 over z, different powers of z? Okay, let's first do z. Okay. Okay, so let's, along the same unit circle, so we're going to plug in e to the it, multiply by the derivative, integrate from 0 to 2 pi. This time they don't cancel. So combine the power. You could still pull out the I in the front. If you find the antiderivative, you can, if you do the u substitution, we'll be dividing by 2i. So I cancels out, but we still have 1/2. And then when we plug in 2 pi and 0, well, e to the 4 pi I, 4 pi I without the t, is equal to 1. So 1 minus 1 is 0. Okay, so this time the integral turns out to be 0. I want to do all the other powers all at once. Let's do z to the mth power and integrate the same circle going counterclockwise. The calculation is pretty much the same. Okay. The only difference being we're going to be dividing by m plus 1 instead of 2i in this case. And when we plug in the endpoints 2 pi, 2 pi n plus 1, that's a multiple 2 pi. So e to the multiple 2 pi I is going to be 1, and 1 minus 1 is going to be 0. So the integral turns out to be 0. So there's something special about the case where we're integrating 1 over z. So when we integrate z to the m along the unit circle, we get 2 pi I when the power happens to be -1, so the 1 over z case, but all the other powers are going to get 0. Any positive power or any negative power that's different from -1. So this is going to be important later. Okay, let's do one more example before we end the video. We can integrate complex functions that are not analytic as well, just the same way. So we can take, let's say we're going to integrate along the curve gamma. So this is a circle of radius r. And then we're going to integrate the complex conjugate function. So let's do that. If we look at the complex conjugate of r to the EIT, the r is real, so the complex conjugate doesn't do anything to it. But the e to the it, so the complex conjugate of e to the it is going to be just e to the negative it, which will cancel with this part of the derivative. So we're just going to get r squared because there's 2 r's here and an I in front. And then we're going to integrate constant 1 from 0 to 2 pi. So we get the answer to be 2 pi I r squared. I'm going to write this suggestively. That is the same thing as 2i times the area of the inside of the circle that it traced around, right? And maybe if you're feeling like playing with some mathematics, maybe you can kind of explain to yourself why this integration gives you 2i times the area of the circle. You might try integrating along different curves that's not a circle and see if we'll get something similar. So that's just a challenge to you, but let's end the video here. I'll see you later.